Alright, here we are in section 8.3, and the process has not changed at all. The only thing that's changed is the nature of our claims. Our claims are no longer about proportions, they're about the mean. And so we'll have to use the context appropriate formula in order to do that. But the first steps, in fact, all steps are exactly the same. So, as you know, our first step is to write the claim in symbols. And so, what we have here in number 14 are data from a data set that's included in the back of the book, and it's about attractiveness ratings of males made by females. And so they give us the summary statistics and they give us a claim. And so we read that claim first. Test the claim that the population mean of all such ratings is less than 7. Okay, so our claim is about the population mean. And so here's the population mean symbol. Let me write that a little bit better. So you remember the population mean symbol is this Greek letter mu, and our claim, I'll just put a C here, our claim is that the mean is less than 7.00. So meaning that no, on the average rating of a male made by a female a day is going to be less than 7. So our null hypothesis we know is whatever the context appropriate symbol is, in this case the mean, the number in the claim, and an equal sign in the middle. And then H1 would be the claim if it could be, and it can. Awesome. So test statistic. Well, no problem calculating test statistic. I can't use this one though. This one that starts with z equals p hat minus p that I've been using all throughout 8.1 and 8.2 is no longer appropriate because it's dealing with percentages. But my claim is about the mean. So I need something with that mean symbol in it. So I'll look for that formula, and here's what we'll find. We'll find that it is not a z anymore, it's a t, and it looks like this: x bar minus the mean. That makes a lot of sense. The separation from the sample mean from this value in the claim, see how far they are apart, all divided by, and this should seem appropriate too, s over root n. This is the standard deviation adjusted for the group size, this bottom piece right there, this s over the root n. And so, of course, that's what our formula is going to look like because we got to compensate for the group. We just plug in what we've been given. So if we look, we've been given x bar. X bar would be the mean coming out from the sample, where if we read, it is 6.19. Mu, that is going to be the null hypothesis value, 7.00. And the standard deviation, well, they have to have given me that, and they did, 1.99. And they better told me how many individuals we were looking at, and we looked at 199 individuals as we did that. So we're going to run this. Be careful how you do that. I type it in as 6.19 minus 7.00 and hit equals. I'm looking at a negative 0.81 divided by, and I use the open parenthesis, 1.99 divided by the square root of 199, and then you can close off that parenthesis, and you come up with a z-score, or sorry, in this case a t-score of negative 5.74. Now t is trying to accomplish the same thing that z is, and that is to give you the number of standard deviations. So that's a pretty healthy number of standard deviations to be away. What's awesome about this section is we can stop right here and go check our answers, make sure we're on the right path. We could look for 14 and realize, oh yeah, its test statistic is negative 1.742. Now they put a 742 in their y's because I'm thinking about a t-score, but remember z-scores in the t-chart are out to 3 decimal places. And so if I look at my number again, it's negative 5.741936. So that would round to the same negative 5.742. Well, it's time to get a critical value. You know that the t distribution is also bell-shaped. You're going to picture having 7 right in the middle. And so if we're going to be less than 7, if I look at my alternate hypothesis and want that to be true, it's going to be to the left. Again, the arrow in the alternate hypothesis, let me draw more attention to that. The arrow is pointing to the left, we're going to be a left-tailed test. And we're going to put all of the significance level in there. And if you remember, our significance level was 0.05. So I can't have any memorized values here because you know that t is dependent upon the sample size as well as the tail area. And so let's take a mental picture of this. We have a 0.05 in one tail, and our degree of freedom is still n minus 1. And if you remember, we had 199 data points minus 1. We're looking for 198 degrees of freedom. So let's go to that t-chart together. So if I come over here, go to my t-chart, bring these charts up and scroll on down. Well, we got to first find 199 degrees of freedom, and it's not going to, or 198 degrees of freedom. Sorry, I said that wrong. It's not there, so I'm going to go to the closest one. So we're going to be in the 200th row, a row headed by the number 200. And then let's come up here, and let's see what column we should be in. Now, if you remember, we had one tail, and only one tail. That's why this chart is split into area in one tail, area in two tails. Because we had 0.05 in one tail, we're going to be here in this second to the last column. So we're going to be in the 200th row, second to the last column. Let's go find it. That'll be the column that's showing right here at the very end as I've narrowed that screen. So 200, second to the last column. Let's make sure we're dealing with the second to the last. We are. 1.653 is what's in the chart. So again, 200th row because the 198 wasn't there and 200 was the closest. The fourth column because that column is the one headed by 0.05 and one tail. So let's take that 1.643 out, and let me just double check something. The 1.643. And so I just want to double check something because I'm seeing something different in the back of the book. I typed something out wrong. Okay. Let me make sure I'm doing this problem the way it's written in the book. So let me come in here and look again. I had typed a 0.05 level of significance. It's not a 0.05 level of significance in the problem. It's a 0.01 level of significance. So let me make that change and we'll look that number up again. I apologize for your time here, but rather than redo the video, I think it's important to realize what just happened. I was checking my answers in the back of the book as I went along, and I didn't match theirs, and it didn't make any sense how far I was off. And so I looked. So it's a 0.01 level of significance, also in one tail. So awesome, dual practice. We're going to come in here, go back to our t-chart, scroll on down. Whoops, gotta make it big. And scroll on down to our t distribution, and we're still going to be in the 198 degrees of freedom, so the 200th row. And where are we going to be? Well, we're not going to be in 0.05 in one tail. We're going to be in 0.01 in one tail. So 0.01 in one tail, 200 degrees of freedom. That's the second column right here. 200 was our closest row. And so we're this number now. Oh, apologize, not that one. We are one below that. I thought I was in the appropriate row, but I wasn't. We are in the blue shaded row. And so we're here at 2.345 coming out of the chart. So as we do that, as we take that 2.345, let's go back to our work, which was number 14. And this is 2.345. Now, if you leave it like that, you should expect to miss a point because there's no way that that point on the left-hand side is positive 2.345. We have to be able to recognize we're on the left-hand side and put a negative. Nobody's going to do that for us. If you're on the left-hand side on a t distribution, you are going to have to put the negative on it because the chart is symmetric. doesn't know whether your point zero 0.01 is on the left or the right, so it's only giving the positives. So if you're on the left, you have to give it the negative. And so that's a good one of the reasons why I picked this problem. So we have that as our critical value, and we're comparing now. Where is the negative 5.742? Well, obviously, it's way off to the left. It's farther away from 0 than 2.345. So we know what we're going to do. That negative 5.742 is in the tail. It's more than 2.345 standard deviations to the left, and therefore we're going to reject the null hypothesis. So the moment we reject, remember your English statement, there is sufficient evidence. And if you're going to then reject the null hypothesis, then there's sufficient evidence to support something. And what you're going to be able to support, in this case, to support the claim. And then just go back to the wording of this sentence. The claim that the population mean of all such ratings is less than 7.00. So we have strong enough data, in fact, or super strong data, to reject that statement, to reject the null hypothesis. Let me not call it the statement. We know it's absolutely not 7. So because we were able to reject that, we know it's to one side of 7. Well, it's to the true side of 7, what was shown in the example, that it's going to be below 7. So there we have, even though 6.19 is only a little bit away, right? 0.81 away from 7. It's super far away from this context, and therefore we know that the mean would never equal 7, and therefore the population mean must be less than 7, since we're seeing it come out less than 7. All right, hopefully that adds to your understanding. All the problems are like this, but I'll do one more in this section.